Hi everyone. In this video, we'll look at something which is famously known as Gabriel's horn, which is an interesting application of an improper integral in the context of a solid of revolution. Consider the region under the graph of y equals 1 over x, where x is larger than 1. I had to cut this graph off somewhere, but imagine this region actually extends all the way out towards infinity. And now imagine this region pops out of your screen and rotates around the x-axis. Pause if necessary to form an image in your mind of what the resulting solid would look like. This solid is known as Gabriel's horn, and it looks like a trumpet except that it goes on forever. So here's the big question in this video. What are the volume and surface area of this trumpet? We know how to answer these questions because this is a solid of revolution, and with improper integrals, we don't need to be afraid of the fact that the solid extends out to infinity. Let's start by calculating the volume. We know the first step is to slice our region into rectangles. I'm going to use vertical rectangles with position designated by the letter x, and with width designated as dx. Horizontal rectangles are of course also possible if you wanted. When we rotate each rectangle, we'll get a small piece of volume that we call dv. In this case, we're rotating around the x-axis. So what type of shape would the rectangle form as it rotates? That would be a disk. To convince yourself of that, pause here and visualize that rotation as necessary. We know disks have a volume of pi r squared dt, where dt represents the thickness, which in this case is dx. R represents the radius of the disk. And if you were able to visualize the rotation, you can see that radius is the same thing as the height of our rectangle. To figure out that height, we need to know the coordinates of the points on each end. And we need these coordinates in terms of x since we're building a dx integral. We know the point at the top would be x comma 1 over x according to the formula for this function. And for the point at the bottom, the x-coordinate would also be x. That's the same x value that was used to position our rectangle. And since this point is on the x-axis, the y-coordinate would be 0 there. Since r is a vertical distance, it can be found by subtracting the y-coordinates of these 2 points, and that simplifies as 1 over x. With that, we're clear to plug in 1 over x as our radius, although to make anti-differentiation easier in the next steps, let's express 1 over x squared as x to the minus 2. Now that we have the formula for dv, we know the volume of all the disks, so all that remains is to add them all up to get the total volume, which is done by taking the integral. In this case, we're adding them up starting at x equals 1 and going all the way out to infinity. After putting in our formula for dv, all that's left now is to calculate this improper integral. So start by taking the antiderivative of x to the minus 2, which you can check is minus 1 over x. And while we can't directly evaluate this from 1 to infinity, we can evaluate it from 1 to t, and then let t approach infinity. Now we plug in each of our endpoints and then evaluate this limit. When t approaches infinity, we know 1 over t will get closer to 0, so this will simplify as pi times 1, or in other words, pi. In conclusion, we found that Gabriel's horn has exactly pi cubic units of volume. Now let's calculate the surface area. That's done by slicing our curve into arc length segments called ds. Here I've drawn one sample segment at an arbitrary point, and we want to imagine each segment rotates around the x-axis to form a ring. We know the surface area dsa of each of those rings would be given by the formula 2 pi r ds, where r represents the radius of the ring. That radius is the same thing as the distance from our sample point to the rotational axis. To convince yourself of that, pause and make sure you're able to visualize that segment rotating around the x-axis to form a ring. Now, to figure out this distance, we need the coordinates of the points on each end. But should they be in terms of x or should they be in terms of y? That's decided by choosing which formula we want to use for ds. Remember that there are two possible formulas for ds. There's a dx version and there's a dy version. I'll choose the dx version mainly because the function given to us is already expressed in terms of x, which means that we want to express these coordinates also in terms of x. For an arbitrary point on this curve, such as the one that was used to position our sample segment, that would be x comma 1 over x. What about the point at the bottom? Well, the x coordinate there would be x. That is the same x value that was used to position the sample segment. And as this is a point on the x-axis, the y coordinate will be 0. By subtracting these y coordinates, we can get this vertical distance, which once again simplifies to 1 over x. So plug in 1 over x as r, and then the only thing we still need is dy over dx. That represents the derivative of our function, and it's easy to check that this is minus 1 over x squared, so pause and verify this if necessary. After plugging this derivative into our surface area formula, we've got everything we need, but a little simplification doesn't hurt at this stage. Now our total surface area will be found by adding up all these surface area slices, starting from x equals 1 and going all the way towards infinity. Plug in your formula for dsa to get this result, which, as you can imagine, this is a really hard integral to calculate. So instead of calculating the value exactly, we're just going to form an estimation here. And the trick to doing that is to notice that this square root represents a value that must be larger than 1. Because under the square root, we're taking 1 plus a positive value. And if you root a number which is bigger than 1, then the result will still be bigger than 1. Therefore, our surface area must be greater than or equal to the integral of 1 over x times 1, which is really just 1 over x. Now this has a really easy antiderivative, which is just ln of x with an absolute value. And we can't go from 1 all the way up to infinity, but we can go from 1 up to t while letting t approach infinity as usual. And if we do this, the surface area we want will be larger than this result. Not necessarily equal, but we'll see that this is good enough for our purposes, so let's just run with this. After plugging in our endpoints, all that's left to do is let t approach infinity. Notice that ln of 1 is equal to 0, so that term may as well disappear. And when t goes to infinity, ln of t also goes to infinity. You can convince yourself of that using the familiar graph of the natural logarithm. Multiplying by 2 pi won't stop this from going to infinity, so we're left with this result. This shows that the surface area we want is larger than infinity, but that means the surface area must actually be infinity. But wait a minute. Let's take a moment to ponder these results. We just found Gabriel's horn has a finite amount of volume, but an infinite amount of surface area. And that's really weird because it would suggest that you could fill the horn with a finite volume of paint, and yet you'd need an infinite amount of paint just to coat the interior. This is commonly referred to as the painter's paradox. And you might think this is total nonsense, but there actually is an explanation for this paradox. Since I don't want to spoil the fun right away, I'll leave it to you to think for yourself or do your own research about how this can be possible. So for now, that's it for Gabriel's horn.